Intel's new 10th gen microprocessors came to the market with their new Sunny Curve microarchitecture with 10 nanometer photolithography. i3, i5 and i7 CPUs comes with this microarchitecture. But if you look at them very closely, you will find that all of these processors have a low base clock speed comparatively. Despite the fact that they have a lower clock speed, they show some very good speed performances. For example, the new i5 1035G1 low-power microprocessor shows a much higher speed performances compared to their 10th gen 14 nanometer processors and its previous i5 low-power processors. If you want to talk about the speed of a computer, obviously it does not depend on a single factor. It depends on multiple factors. For example, speed depends on the computer's random access memory, the RAM. Higher the RAM, faster the speed, and so on. And the speed depends on other factors such as the CPU, and secondary storage, whether you're going to use a mechanical hard disk or solid state drive, etc. But imagine all of these factors held constant except CPU, then the speed depends primarily on the CPU. And our discussion is now one was based on the CPU and its design architecture. Well, if you talk about the CPU, we need to talk about three main components: the processors, the register structures, and the cache architecture. The processors consist of the ALUs, the control unit, and the clock. Higher the clock speed, faster the instructions being executed. But it is not the most critical factor for speed. The speed often depends on the registers and the cache architecture rather than the raw clock speed. To understand this, let's find out how everything works together. So the processor is the fastest, but it can't work on its own. It needs to access instructions and data, which is held inside a register file. But the register file is very small in storage size, often in the range of several kilobytes. So it can't store all the instructions and data needed to be executed. So the register files needs to access a little bit larger storage called primary cache, L1, which can store more information but a bit slower than the registers. Then this L1 can access a larger storage element called L2 cache, which is larger but slower. Then the secondary cache can access the RAM, which is significantly larger but slower than the cache. Then the RAM can access information from the hard disk, which is the slowest. The processors, registers and caches are inside the CPU, and therefore the performance of a CPU greatly depends on the cache and the register architecture. Let's say the processor needs to access some bits of information and it can't find it inside the register file. Then the processor needs to access the cache. If it is also not available in the cache, then it needs to be accessed through the RAM. The information goes from the RAM to the caches and then to the register file and then to the processor. Now let's say the processor has a clock speed of 3 GHz. Now for simplicity, let's imagine the processor can compute 1 instructions in 1 clock cycle. So ideally, the processor can compute 3 billion single instructions in every second. But this can happen only if the processor can access all the information needed in its register file. But the register file is extremely small in size and the processor often needs to access the cache. But that would require 1 or 2 additional clock cycles. But in some cases, the required information cannot be found even in the cache, so the processor needs to access the RAM. But that would require astonishing 100 additional clock cycles each. That means the effective speed reduces to 100 times less than the 3 GHz clock speed.
So the computer speed not just depends on the raw clock speed, but it also depends on the cache architecture. The amount of cache misses is significantly important for the performances.
Therefore, if you compare a processor of 3 GHz clock speed with a slower cache architecture and a 1 GHz processor with a much faster cache architecture, more often the processor with the fast cache architecture wins the race. And if you compare the Intel's 8th or 9th gen processors with the newer 10 nanometer 10th gen processors, you will find that the newer 10th gen processors have better L1 and L2 cache architectures, while the 8th or 9th gen has 4-way set associative L2 cache architecture. The newer 10th gen has 8-way associative L2 cache architecture. This is why the newer 10th gen 10 nanometer processors are faster even with relatively lower clock speeds.